Welcome to this video on the Electronic Total Station, or ETS. The total station is an important instrument used in modern land surveying for accurate and efficient measurements. In this module, we will learn about its components, working principle, functions, accuracy, advantages, limitations, and applications in land surveying. Let us begin.
Our learning journey is divided into 8 key areas. First, we will understand the basic concept of an electronic total station. Next, we will identify its major components and understand how each component contributes to the surveying process. We will then look at the scientific principle behind distance measurement, followed by the measurement and calculation functions of the instrument. After that, we will discuss accuracy, the standard field operating workflow, and the major advantages and limitations. Finally, we will explore how total stations are used in surveying, mapping, construction, engineering, monitoring, and other applications. So, what exactly is an electronic total station? An electronic total station is a modern surveying instrument that combines 3 important capabilities into a single field-ready system. First is the Electronic Distance Measuring Unit, commonly known as EDM. Second is the electronic digital theodolite, which measures horizontal and vertical angles. And third is an onboard microprocessor and memory system, which processes, calculates, and stores survey information. Together, these systems allow the instrument to measure angles and distances, calculate coordinates, and record survey data digitally.
Let us now look at the major components of an electronic total station. The telescope is used to precisely sight the target. The EDM unit measures distance by transmitting electromagnetic signals, such as infrared or laser-based signals, towards the target. The processor acts as the computational center of the instrument. It processes measurements and performs the necessary calculations. The display provides the surveyor with measurement values, settings, and calculated information. The data storage system records the observations and survey data for later use. The reflector, commonly used as a prism, reflects the transmitted signal back towards the instrument. And finally, the battery provides the electrical power required for field operations. These components work together as one integrated surveying system.
This labeled view helps us understand the physical arrangement of the major components of the total station. For a surveyor, knowing the instrument anatomy is important not only for operation, but also for proper handling, maintenance, and troubleshooting. Before using an ETS in the field, the survey team should be familiar with the location and function of its essential controls and components. Now let us understand the basic principle behind electronic distance measurement. The distance between 2 points can be determined when the velocity of the signal and its travel time are known. The EDM unit sends a modulated electromagnetic wave towards a reflector. The signal travels from the instrument to the reflector and then returns to the instrument itself. The system determines the travel time of this signal. Using the known signal velocity and the measured travel time, the onboard processor calculates the distance. The important point to remember is that this entire process takes place electronically, and the result is made available to the surveyor almost instantly.
An electronic total station is much more than a distance measuring instrument. It performs a range of measurement and calculation functions. It measures horizontal and vertical angles between reference points. Using EDM, it measures the distance to the target or prism. It can also assist in determining the height of points or objects. Once these observations are available, the onboard system can calculate the 3-dimensional coordinates of points, commonly represented as X, Y, and Z. Based on these coordinates, the instrument can also perform calculations such as area and volume. This combination of measurement and computation significantly reduces the amount of manual calculation required in the field.
Accuracy is one of the most important considerations in modern surveying. The accuracy of an electronic total station depends on the instrument specification, calibration, environmental conditions, and the skill of the operator. The presentation indicates typical angular accuracy in the range of approximately 1 to 5 seconds, while distance accuracy may be expressed in millimeters, together with a parts per million component. Positional accuracy depends on the combined effect of angular and distance measurements and the survey methodology. It is important to remember that instrument accuracy alone does not guarantee survey accuracy. Proper setup, calibration, observation procedure, and field conditions are equally important. Basically, factors such as temperature, humidity, and atmospheric pressure may influence measurements. Operator error during centering, leveling, sighting, or observation can also affect the final result. Let us now look at the typical workflow for operating an electronic total station in the field. The first step is pre-operation checking. Inspect the instrument, check the battery, and verify that the system is ready for operation. The second step is setup and leveling. The tripod must be positioned securely, the instrument mounted properly, and the instrument carefully leveled. The third step is measurement. The surveyor selects the target point, sights the target, measures angles and distances, and obtains the required coordinates. The fourth step is data management. The observations are stored in the instrument's memory and can later be transferred to a computer for processing and analysis. Finally, after fieldwork is completed, the instrument should be properly shut down, safely stored, and maintained. Electronic total stations offer several important advantages. First, they provide high precision in angle and distance measurement and reduce the scope for manual calculation errors. Second, they improve field efficiency because measurements and calculations can be performed rapidly. Third, digital data collection improves overall productivity by reducing manual recording and data entry work. The ability to store and transfer large volumes of survey data also makes digital data management easier. Total stations are versatile and can support applications ranging from topographic and boundary surveys to construction layout and monitoring. Reduced dependence on paper-based recording can also contribute to more efficient and environmentally responsible field operations. However, like any technology, an electronic total station also has limitations. The initial cost of the instrument can be relatively high. Effective operation requires trained personnel because incorrect setup or measurement procedures can introduce errors. The instrument depends on electronic components, software, and battery power. Therefore, technical problems or insufficient battery capacity can affect field operations. Environmental conditions may also influence measurement accuracy. Since survey information is stored electronically, proper data management and backup are important to reduce the risk of data loss. Finally, regular maintenance and calibration are necessary to ensure that the instrument continues to perform within its required accuracy. Electronic total stations have applications across a wide range of surveying and engineering activities. In surveying and mapping, they are used for topographic surveys, boundary surveys, and mapping activities supporting urban planning and infrastructure development. In construction and engineering, total stations are widely used for setting out, layout, as-built surveys, and monitoring structures such as buildings, roads, and bridges. They are also used for monitoring and deformation studies, where movement, settlement, or structural changes need to be observed. In geological and environmental applications, total stations can support mapping, environmental monitoring, and natural hazard assessment. From defining land boundaries to supporting infrastructure development, accurate survey measurements provide an important foundation for spatial decision-making. To conclude, the electronic total station represents an important advancement in modern land surveying. By integrating electronic distance measurement, angle measurement, onboard computation, and digital data storage, it enables surveyors to collect accurate spatial information efficiently. For effective land surveying and land governance, however, technology must always be supported by proper procedures, trained personnel, calibration, and responsible data management. The quality of a survey depends not only on the instrument, but also on how accurately and systematically it is used. Thank you for joining us in this learning module on the electronic total station.